Well, it's a great pleasure for me to join this forum today, and I'm going to try to rush through my presentation. I know the chair of the session is very tough with giving the time. So, at the turn of the century, robotics has evolved from this image that was a robot working in a structured environment in an industrial setting to robotics coming closer and closer to the human. And as we see in all these applications, robots are interacting with human. The human is operating robots in a surgery. The robot is interacting with school children. The robot is assisting the elderly. And clearly, robotics is coming closer to a human being, and that is bringing a lot of challenges and a lot of interesting research problems in robotics. Well, the first thing we should consider is, are we really ready to bring those robots next to us? That is, do we have the safety that is guaranteed in those systems so that we can really have a clear interaction? And if we take a human, and if we think about the safety of a human interacting with others, we are going to look at the impact forces, and those are determined by the effective masses moving when the human is moving or launching an object. Well, if we look at the human numbers, we see the index of safety is about 0.034, whereas a small robot like a Puma would have a number of over 50 times higher. And this is really the problem that comes from the way we design those machines. Well, over the past years, we started all around the world looking at new concepts of designing robots that will reduce those numbers so that robots can be really safe to interact with the human. And I will probably have the chance later to mention what we are doing at Stanford in that area. Do we have skin on those robots? Are we able to sense and determine the direction and contact point? Do we have robots that are capable not only of walking? We saw a lot of humanoid robots capable of going upstairs and moving, but are they able to interact with the world? Are they able to make contact with the world without falling? So these are challenges that brings new problems in terms of the perception, that we need not only perceiving the free space, but we need also to perceive the contact. We need tactile feedback. We need to deal with a lot of new challenges, dealing with the mechanism in terms of the performance and the safety. We need to deal with the perception and sensing for worlds that are unstructured. We need to deal with the planning and control. We need to deal with skills for the human. We need to deal with the human-robot interaction. We have a lot of fun with many interesting problems that brings together interactivity and human-friendly robotics to those applications. So I'm going to talk a little bit about some of these issues in the remainder of the time, but safety is really critical, and unless we deal with it, we're not going to be able to deploy those robots. And safety has been dealt with by separating the workspaces of the robot with the human. And now we are saying we are going to bring these robots to the human environment, so safety is critical. Now, performance is also critical, and the two are always competing. How can we deal with this problem? Well, we designed a new robot that break the concept of one motor per joint. We broke the motors through a frequency requirement and showed it is possible through macro-mini actuation to build mechanisms that are safe. And this is an example of a new concept of designing hybrid muscle-like actuation on bones together with electrical motor and skin all around the arms to build an arm that is completely safe for interaction with the human. And we, in fact, are building currently the skin and developing the sensors together with the actuation. On the control aspects, we have challenges that come from the fact that we have combined mobility with manipulation. These are some early development. Romeo and Juliet were two robots that we built at Stanford almost in the early 90s. And those robots brought a number of capabilities in terms of combining mobility and manipulation. Well, by the end of the 90s, Honda brought a robot, all of you have seen, and we were asked to take the capabilities of interaction of Romeo and Juliet to robots like this one. Well, that is not easy because we are talking now about multiple robots that brings new structures with many more degrees of freedom and many more difficulties in the control and the interaction. We need to deal with a very clear problem, which is a task, and this task involves contact and motion. But as we do those motions while in contact, we need to deal with constraints. And constraints are internal obstacles outside. But even then, you still have more freedom. You have the posture of the robot. And this posture has to be consistent with everything we listed. So it has to be consistent with the task and the constraints. That brings about a controller that requires whole body control, but also dealing with the constraints, dealing with the contact, and dealing with the skills of the robot. And this is something that we would like to be also skill-like, human-like skills. So we started learning from the human, we started analyzing human motion, we started applying techniques from robotics to the analysis of human. In fact, what you discover working with robotics is that much of the body of science we develop in robotics is not only good for robotics or good for robots, it's good for articulated body systems. Many of the algorithms are very useful in other domains, modeling the human, and we started modeling the human to understand robots and to capture the way human moves so we can map it to the robot, but then we were able to apply it to the robot, but also to the human. So now we have these models that can analyze athletes that are moving, and we can have their motion captured, analyzed, and then we can map their characteristics, and then we can close the whole loop that is from motion capture in real time. We can analyze the characteristic and do feedback to the human to make corrections. Skills brings us to the interaction, and the interaction brings us to the haptic interaction that is essential in order to produce those motions. I have only two hands, and I'm going to try to show you a haptic on my laptop. Here is a simulation of the haptic without the haptic device. I'm going to operate this gel by moving this object, and you can see the forces on the right, but you can also see the interaction with a flexible environment, which is very difficult to do, and this is running actually on the laptop. Now, once we have that feedback, we can go and touch physical environment through another robot that is, so the haptic device is driving the virtual robot and driving the model and then driving the real robot. And then we reconstruct what the robot is sensing. And we are at the same time dealing with the constraints of detecting the collision, resolving those collisions. When we have these collisions, we need to dynamically resolve them. And here we see how we are doing this in real time. We are resolving thousands and thousands of collisions in real time, which can be used to analyze crashes. For instance, test crashes could be done in the computer. Or if we are using the haptic to interact with human, we can do all kinds of things. Like in this project, we are looking at ultrasonic imaging of pregnant women, where we are getting the images and reconstructing those images and replacing, in fact, assisting the sonograph, which usually suffer a lot from the pressure of these measurements. So here we are doing it on the hand or the arm of one subject, and then we do it on a virtual womb. So we are scanning now the baby, and what is happening is that we are going to have the 3D image reconstruction of that environment. And this is what the ultrasonic imaging is producing. And step by step, we build the whole model, and now we can examine this model. Haptics is very important, and it can be applied in space. This is an experiment with NASA exploring how we can do haptic in the zero gravity. And in fact, all of this cannot be done without dealing with all the constraints. Let me just show you how we deal with constraints. For instance, we have this robot here, and if there is an obstacle, we need to take that obstacle into account. So you can see how the robot is moving away, and moving away by getting away from this obstacle while maintaining the task. This is critical to be done in real time in order to achieve the capabilities of interactivity that we are talking about. So once we have those problems resolved, then we are still need to put, in addition to the constraints, the balance, the multi-contact. So how we control those multi-contacts, they are also treated in the same way. And again, I can show you here how we can do that with the simulator. So here is the robot is currently balancing between all these contacts, but if we pull on the robot head, you can see how immediately there are adjustment of all the points to recompute the reaction forces and distribute them at all these locations. This is very important if we want to be able to be doing those interactions in real time. And once we have them working, everything is going to be working well. But if you do not measure contact forces correctly or make any mistake, the robot immediately will break the contact and produce instabilities. This was implemented on Ashimo. Actually, we have one Ashimo at Stanford, and you can see here Ashimo performing motions, while in fact we are moving the table and putting different objects in front of Ashimo. I'm not going to run the video, but this work is part of a bigger picture of how we build architectures for computer systems that integrate artificial intelligence together with controllers by building unified framework for whole body control. And in here we can see an example of a very complex behavior that is all implemented through just a unified vector that is sent to the controller. As you know, in the Bay Area in California, the housing is very expensive, so we bought a virtual apartment for our robot, where we are exploring in the virtual world a lot of skills and developing those skills and then implementing them to the robot. So here is the robot is performing different tasks, doing balances. Thank you very much, and let's go.
Thank you.
Thank you.